Hello. So this lesson is 4.1, the last page of it. Many real-life situations can be described using exponential functions, including population growth, people, animals, microbes, etc., growth of epidemics, radioactive decay, and other changes that involve rapid increase or decrease. And sometimes these changes are modeled using what we call the natural base, which is the irrational number e. So e on your calculator is going to be above ln. So right there you can see is e to the power of x. And now we want to round the value of e to the power of 1 to 2 decimal places. So e to the power of 1 equals 2.72. The 1 goes up because the number to the right is greater than 8. What is the other irrational constant found on your calculator that we are more familiar with? Well, that would be pi. And we've round it to 3.14 normally. Okay, so let's look at this. We've got compound interest formula, which is this one here, and then we've got compounded continuously. So what do these mean? So A is what the amount that we have after the interest has been compounded. P is the amount that we had originally, so it is called the principal. R is our rate, and our rate is a lot of times it's given as a percentage, but we want it as a decimal, and it is an annual rate that is given most of the time. N is the number of times compounded, and T here is time, and normally it is in years. So let's look at this first example. If you are given $10,000 by Auntie Gerda and decide to invest it at an annual rate of 5.5%, how much money will be in the account after 5 years if it is compounded monthly? So our principal, the P, that is the given money, so that's $10,000. Our rate is 5.5%, which again, we need to convert this to a decimal, which means that we are dividing by 100. So 5.5 divided by 100, and actually this percent means dividing by 100, so we leave that out. And we can use a calculator, or we can move the decimal. We're dividing by 100, so there's 2 zeros, so we move the decimal 1, 2. So 0.055 would be the rate as a decimal. Our N compound, the number of times compounded. So it says compounded monthly. Well, that means that we are compounding it 12 times a year. So we have 12 months, so it is compounded 12 times a year. And our T here is the 5 years. So now we have all the information we need, and we're going to use this formula here because we're not compounding continuously. So $10,000 times 1 plus our rate 0.055 divided by n, which is 12, to the power of n, which is again 12, times our years T, which is 5. So let's put this in the calculator, and you've got to be very careful with the parentheses here. 10,000 times 1 plus 0.055, parentheses closed, to the power of, and I'm going to put this inside parentheses as well, so that for sure all this is the exponent. So we get, something's not right. Haha, now I know. I think I know what I did. So my mistake is that I didn't divide this by that 12. So yeah, like I said, make sure you're careful. $10,000 times parentheses. Other 5 didn't. Divided by 12, parentheses closed, to the power of, again, I'm going to open parentheses, 12 times 5, close them, and hit equal. Okay, that looks better. $13,157.04. Again, the 3 goes up because 7 is greater than 5. Okay, next one. What if it is compounded quarterly? So everything else stays the same except the n. So here we compounded it monthly. Now we're going to compound it quarterly, which means that n is going to be 4. We use the exact same formula. So $10,000 times 1 plus 0.055 divided by 12. Not 12. That was where we want to put the 4, the n, to the power of 4 times 5. Our years stay the same. It's only the 4 that changes. And now we, again, use the calculator. $10,000 times 1 plus 0.055 divided by 4, close the parentheses, to the power of, and again, I'm going to put this inside parentheses, 4 times 5. If I don't put it inside the parentheses, it's going to think that 4 is the exponent and then multiply everything else by 5. That's the reason why it needs to be. So our answer is 13,140.67. So as you can see, if we compare these two, when we compound more times, so when n is 12 compared to 4, we do get more money. Now, next one. What if it is compounded continuously? So now we're going to use this here. So again, we have the same principle. So P is $10,000 times E, the natural base, to the power of our rate, which is 0.055, times T, which is our years, 5. Okay, so let's put this in. 10,000 times the E, so I have to press the second and E, or the second and ln. And it opens parentheses, so 0.055 times 5, close the parentheses, and hit equal. So if we compare all these three, we can see that this is the largest number. So if we're compounding continuously, we get the most money. Okay, let's look at this next example. So we have the annual amount of energy produced in the United States from dry natural gas in trillion cubic feet can be approximated by the function g of t, where t equals 10 corresponds to the year 2010. Find the amount of dry natural gas energy produced in 2000. Well, so if t equals 10 is 2010, so then the year 2000 is going to be t equals 0. So we're going to calculate g of 0. 14.66 times 1.042 to the power of 0. Well, any number to the power of 0 is going to be 1. So we're going to left with 14.66 times 1, which is 14.66 trillion cubic feet. And that is our answer. So that is the year 2000. Now B is asking to find the amount of dry natural gas energy produced in 2015. So our T is 15. Oops. T is 15 now. 2000 minus 2015. So G of 15 equals 14.66 times 1.042 to the power of 15. And now we're going to need to use the calculator. So 14.66 times 1.042 to the power of 15. It is 27.17. And that is, again, trillion cubic feet. So, next, if the model continues to be accurate, project the amount of dry natural gas energy produced in 2022. So, 2022 minus 2000, we're going to end up with T equals 22. So, G of, oops, not 15, 22. I was looking at this number here. 14.66 times 1.042 to the power of 22. 14.66 times 1.042 to the power of 22. 36.24 trillion cubic feet. Okay, that's it for this lesson 4.1.